In the last class, we introduced what is called a Hilbert space. Okay? So H is a Hilbert space. By this, we mean there is an inner product, which is a function of two variables from here to C, which I already listed all the properties. It is linear in the first variable. You can take a scalar out, you can take a sum out, and conjugate linear, the complex variable. You can take it out as a bar, conjugate linear in the second variable. And it satisfies this condition, xx is greater than or equal to 0. And this is what we call as norm x. And this gives norm x, norm x. This gives rise to a norm. And it is also true that xy equal to yx bar. This gives rise to a norm. And with respect to this norm, H is complete with respect to this norm. As a metric space, this norm gives rise to a metric, and that it is complete with respect to this norm. Then we call it a Hilbert space. It's just an inner product space which is complete with respect to the induced norm. When we defined an orthonormal set, I mean, we use natural number because, we use natural number as induction set because it will be separable. I mean, it may be infinite. Okay, let's set to be orthogonal. A set is orthonormal if each x in S norm x equal to 1 and xy inner product is 0 for all x not equal to y. Okay, this is what is called an orthonormal set. Then we proved if H is we proved if H is separable. The other way is also true. Let us come to that later. H is separable implies any orthonormal set is countable. It's at most countable. At most countably infinite. We proved this. Okay. So this is an exercise. Okay, I will prove it. It's easy. Proposition. Did I do this? Any orthonormal set is linearly independent. Did I say that? Okay, we proved that. So any orthonormal set is linearly independent. We have proved that. And further, if something is orthonormal, let's say just yn orthonormal, then summation to this n equal to 1 to infinity, the inner product of x en norm square is finite for all x elements. In particular, this implies we proved that in particular we proved that x en goes to 0 as n goes to infinity. Okay, we proved all these things. So now we want to see some more properties of Hilbert space. That En H is Hilbert space as usual. We want the completeness. Okay, so H is Hilbert space. And we have orthonormal. And we also have some sequence, some complex number, sequence of complex numbers. This. Then the following are equivalent. Following statements are equivalent. One. Summation alpha n n equal to 1 to infinity, converges in H. H as a norm, H as a metric, and it converges in that metric. Okay. It is equivalent to saying summation n equal to 1 to infinity mod alpha n square is finite. So these are positive numbers, so this makes sense. This is finite. This is equivalent to this. Then third thing is there exists an X in span. You take the span closure of all those En, and yeah. You take the closure in the inner product or norm. Okay. Take the closure. Okay. Is it such that inner product of X En equal to alpha? Okay. Proof. So one says that series converges in H. So it's a Hilbert space convergence. Whatever it is, by that we mean this is a Hilbert space. Convergence is equivalent to saying that it's Cauchy, right? This means, this convergence means that is we have n equal to 1 to n, alpha n, En converges as n goes to infinity. This is equivalent to saying summation n equal to 1 to n, this sequence, this 1 to n is Cauchy. Because we are working with complete norm linear space. So this is equivalent to saying, let us put equivalence. Maybe 1 equivalent to 2. We'll prove 1 equivalent to 2. Okay. This is equivalent to saying summation n equal to n 1 to n2, okay, alpha I, alpha n, En goes to 0 as n1, n2 both goes to infinity, which is of course equivalent to saying norm goes to 0, right? That's what it means with something goes to 0, which is equivalent to saying norm square goes to 0. But this norm square is nothing but summation n equal to n1 to n2 mod alpha n square, right? This is precisely equivalent to saying n equal to alpha n square is right. This series of positive numbers converges if and only if n1 to n2 this goes to 0 as n1, n2 both goes to infinity. Okay. And the converges Cauchy. This is the property of the orthonormal set. Usually we will say that something converges if and only if the norm converges, right? That's what. But here norm square. Hilbert spaces, it's with norm square. Okay. So we have proved 1 is equivalent to 2. So we want to prove that 1 and 2 both are equivalent to. We want to prove that that is equivalent to 3. First one is there exists a X such that first we want to prove this implication. Suppose if this converges, summation alpha n, then call this xn equal to summation n equal to 1 to infinity alpha n En. Then x En, of course, if you take the inner product, incidentally, shall I give it as an exercise or okay, assignment? I gave some assignments on stone vesta. No. What did I stone vestas? Stone vestas, okay, locally compact, I gave that. So this is assignment. Prove, maybe we've seen this earlier, but it's important to do this. Prove that inner product is a continuous function on 2 variables. Inner product is continuous. You have to take the norm and work with that. I mean, if xn converges to x, yn converges to x, xn, yn, then the product converges to x. So you take the modulus and use inequality. Inner product is continuous. Then you have xen, you will have the summation n equal to 1 to infinity. Since the inner product is continuous, you can take the, you can take the sum and infinity out. Of course, inner product is linear and continuous, so you can take that out. Okay, and then xen will only for n, only for that n it will come survey, right? This is equal to alpha. That's what that statement is. Okay. Now to prove the other way, so this way is clear. Now to prove this way, suppose there exists x in span closure of en, n in n, such that xen equal to alpha n. We have already proved that for any x, for any orthonormal set, summation I have written there. Then summation mod alpha n square equal to summation mod xen square. This is finite. We have already proved. In the last class, we have proved. Okay. So that's what 2 is. So 1 is equivalent to 2, and 1 and 2 are equivalent to this. Okay, so the proposition is true. So we want to define what is called an orthonormal basis. This, remember, you should remember, this is not basis. Basis for a vector space is an algebraic object. Okay, you have a subset of a vector space whose finite linear combination. There is no infinite. You can't talk about infinity because you have to take limit. Then you have to define limit. There is no topology. There is no metric, so you cannot talk about limit. So it's just an algebraic statement. Okay? A basis is an algebraic statement. But this orthonormal basis I'm going to define is a topological statement. Okay, it will involve convergence. Okay? I'll write the proposition. Any subset satisfying this is called an orthonormal basis. Okay, that En the following statement. 1, you have some En is a maximal orthonormal set. That is, there does not exist a set bigger than this. Where this is strictly, that is, if you have E is this, you call this E is this. E is not contained in, E is not strictly contained in a bigger orthonormal set. The maximal orthonormal set. That is what we call as a basis. Okay. 2, every element in the Hilbert space H can be expanded by this. X equal to summation. You take the inner product, you take that component. It's like if you have a X, you take the X component, Y component, and if you add it, XEA, it's like an Rn. You have X, Y, and X times this vector, 1, 0 vector, 0, 1 vector. That's an orthonormal basis. It's exactly the same state. En. Okay. The convergence is in that Hilbert space convergence. Okay. For all X. Okay. 3, for all X, Y in H, if you have 2 of them, then you can compute the inner product like this. It is equivalent to this. Summation n equal to 1 to infinity. You take this inner product. and you take this inner product. This is just a particular statement of this, which is this norm x square equal to summation or x en square for all x. Okay. This is all these things are same as h is equal to, I mean, this is just, it will follow from all the statement. Let me just say this, span closure of En. This orthonormal basis, you take the span, it gives a dense subspace of H, okay, which is clear from this, right? First statement itself is clear. Okay, so there is nothing. But the other way you have to prove, other way will also be clear. If you take, if you can write something as the basis, then you can take the, I mean, this is an exercise. Anyway, we'll see that. Okay, so proof one by one. One implies two. Now, incidentally, any, okay, I will write it after proving the proposition. One implies two. If you have a maximal orthonormal set, then you want to prove this. It can be expanded through the En. That's what you want to say. Okay. So we already know that this converges. We already, the earlier proposition says that if summation sum alpha n square is less than infinity, then alpha n En converges. Okay, we already know that xen mod xen square converges for any orthonormal basis. So summation mod xen En converges. Okay, so by previous proposition, that x naught equal to summation n equal to 1 to infinity x En okay, which converges by previous proposition, which converges, not just previous proposition, what we have proved earlier. We have proved that summation mod square of this is finite, and by the previous proposition, this converges. Now the claim is this x naught is nothing but x. That's what we want to say. Okay. Now x equal to x minus x naught. You want to prove this is 0. Okay. Now x equal to x minus x naught. This is, you take the inner product with any En. Then inner product of this x minus x naught with any En. You just have the summation again. You just insert this x minus x naught, okay, which is just, I mean, x minus x naught is orthogonal to all En, right? Right? X naught is this. X naught inner product En is just xen. And if you take the inner product is xen minus xen is 0, right? Because the inner product is linear and continuous using all that, this is clear. So this is equal to 0. So x naught is orthogonal to all those En. Okay. And if it is not equal to 0, then you can have a bigger orthonormal set, right? If x minus x naught is not equal to 0, then En, n in n, union, this set, x minus x naught, maybe you want norm 1, so norm x minus x naught, which is not equal to 0, is orthonormal set, okay, which contradicts the maximality of that. We assume that there's a maximal orthonormal set. It contradicts maximality. So x equal to x naught. Okay? That's what you want to prove. Now, 2 implies 3. So when you can expand it like that, then that is just 2 says that x equal to summation x en and y equal to summation y en. That's what 2 says, right? Now you take the inner product between them, xy. Maybe here m. Okay. Right? Now inner product is continuous in both the variables. Okay. You can take the inner sum out, everything out, and you will get only this en, but only when n equal to m, it will survive, otherwise it is 0. And you can see that, but when n equal to n, it is just norm is 1. Norm of en square is 1. So if you use all that, when you take it out, you will get an inner product between en and em, which is delta n and m. So this is equal to summation. And if you take this out, this will come as a bar, right? But that is equal to E and Y. That's what you want to do. Okay. And the fourth statement is just take x equal to y. Right? Then x en x. This is just the bar of that. So norm of x en square. Now we want to only we are left with only 4 implies 1. We are left to prove only 4 implies 1. So 4 says that any x, I mean 4 says we have, let's write what is 4. Norm x square equal to summation mod of x en square for all x. And we want to prove this en is a maximal family. There is no other maximal orthonormal set. There is no bigger orthonormal set than that. Okay. So suppose it is not maximal. Suppose en is not maximal. That is, there exists a E which is orthogonal to all these En. Right? That's what it means. But then we know that it satisfies this. E also satisfies this. Norm E square equal to summation E En mod square, which is equal to 0. E is 0, but E should have norm 1. Okay. I mean, it's an orthonormal set, so norm it should not be 0. So E equal to 0. That's all. So En is maximum. Okay. So we have proved the proposition. So if you have a maximal, and finally, the fifth one, what I say is the span is this. It's clear that, I mean, if it satisfies one of this condition, then it's going to, any x can be written like this. So it is in the span. Any x is in the span. Suppose if every x is in the span, okay, then this En is maximal, we want to say. Okay, if 5 implies 1 or something. I will leave it as an x. 1 implies 5 is clear. Okay. because 2 implies 1 is equivalent to 2, so 2 will imply 5. Okay, 5 implies 1. So if xn converges to x and xn is equal to summation alpha I equal to 1 to some number n. I mean, it depends on n, okay? Everything depends on n. It just looks like this. Let's just write it like this. Okay? Then en, I'll say xk, sorry, xk. Let me say xk. I mean, I want to prove 5 implies 1. 5 says that the whole Hilbert space is span closure of this En. So I take any arbitrary x that will have an xk convergence to S where xk is of this form. Now, if we take the inner product with En with xk, that is 0, right? Because it is of this form. No, it's not 0. What do you want to say? I want to say it's maximal. Sorry, maximum. I want to say 1. If E is orthogonal to En, E is orthogonal to En, n in n, okay, then E inner product of this xk is 0. Okay. This implies Ex equal to 0 for all x in H. In particular, E is 0, which is norm U square equal to 0, so E is 0. Okay. Can we write it? Should I write it again? It's clear, no? I mean, I wanted to leave it as an exercise, but okay. So all these statements are equivalent statements. So here, as you see, it involves the topology. This is just you take the span, finite linear span, and you take the closure. Okay, so it's not the usual basis. It's some special. It's the topological basis. It depends on the topology. This is what is called any En satisfying this condition. One of these conditions is called an orthonormal basis. This is definition. Any En n satisfying 1 to 5 in the earlier proposition, in previous proposition, is called an orthonormal basis. Orthonormal basis. We write it ONB, orthonormal basis. Okay. Right. Right. You are not listening. I repeated 2 times. This is not the usual basis. This is an orthonormal basis. It's a topological statement. It's not an algebraic statement. I started the class with that. It's not? It's not? Yeah. It's not algebraic sum. That's what I said it 2 times. That it's algebraic basis is finite linear combination will give every element. Here you have to take all finite linear combination, then close it. It's a topological statement. Or you can expand it in infinite sum. I mean, even if you take finite linear combination and the closure is everything, that doesn't mean you can write everything as a infinite sum. For example, polynomials are, you take the finite linear combinations of polynomials and that evidence in C of x, okay, or even finite linear xn, x power n. Okay. So, but then you cannot write everything like that. You cannot write like everything like that. So, this is something special for orthonormal basis. You can write it as an infinite sum, where the infinite sum makes sense in the norm topology, the topology. Okay. What else? That's all. So let's start the Fourier analysis. We want to use this tool. I mean, this is just our tool for to make a statement on Fourier analysis. Okay. So we will work with the following H. Before that, I earlier defined this. I put a 0. So this C0 is functions vanishing at infinity in a locally compact space. I put a 0 on the top. Hope it's okay. Okay. So 0 of this interval 0 to pi. all those functions in C of 0 to pi with coincides in the endpoints. Okay. This is just continuous functions on 0 to pi where you identify the endpoints. I mean, this is what is called a quotient space or something. Quotient space is where you can identify a whole set with as a point or something. You will get a quotient topology, and I don't want to go into that. Okay. So this is actually isomorphic to C of the circle. Circle, what notation shall I use? I use dou D or T, D. Okay. Boundary of the disk, complex disk. Okay. This is nothing but T of this. This Z in C mod Z equal to 1. Boundary. Disk is mod Z less than or equal to 1. There is a boundary of the disk. Okay. Now, usually the key, some key is written. I'm usually confused with that notation. I may not write it properly. So, sometimes I write this also. Okay. Both are same. Okay. It is the complex circle. Circle in the complex. Unit circle. And you can identify anything with here. Just you take, I mean, which is an algebraic isomorphism, which preserves the norm, infinity norm, everything. That is, if you take a f in C0, 0 to pi, you define f tilde in C of this by f tilde at e power it is nothing but f of t. That's all. E power it, everything will look like e power it. And f of e power it is f of t for t in 0 to pi. Then it will coincide on 0 and 2 pi. Because the constant coincide on 0 and 2 pi, these two are same. And this is the same function. Okay? And the supremum will coincide, everything will coincide. So there is no difference between these two algebra. Okay? Same algebra. So we identify these two algebra, and mostly for integration and other thing, we will work with this. Okay? But remember, these two are same. Okay. Our Hilbert space H is, incidentally, I talked about orthonormal basis. Why should it exist? It exists because of Zorn's lemma. If you have one single element, that is orthonormal set. It's a single element of norm 1. That is an orthonormal set. Okay? Then there is no other element, so it should be, I mean, the conditions are this. Given any orthonormal set, you can extend to I mean, you given any orthonormal set, you can, I mean, you can, if you have another element, linearly independent element, which you should be able to find, you can, there is a Gram-Schmidt orthogonalization. You can make it, you can get a bigger orthonormal set. Now you consider all orthonormal set and put the partial order, one is subset of that, there will be a maximal element. That maximal element will be orthonormal set, and we don't need all that because we are going to explicitly going to produce an orthonormal basis. So we don't need, we are going to work with one single orthonormal basis for this. Our H is to take L2 of 0 to pi, which is also same as L2 of that dou D or whatever you want, which is just the completion of this. Completion. Is it okay if I define it like that? I forgot to say, I mean, I already defined. Let me first define. Sorry. We have already seen this, but let me define again. Define inner product FG2 equal to integral f of t g of t bar dt. Okay. On 0, 2 pi. This is genuine inner product. We have seen it in the first class. Okay. On any interval, this is genuine inner product, and it's positive. For continuous function, integral norm f square equal to 0, then norm f is 0 as a continuous function. So this is an inner product, and so our L2 of this 0 to pi. This is just the completion of this with this inner product or norm 2, whatever. You know, this is also a function space actually, but you don't have to worry about it. In fact, we don't worry about this L2 0 pi. It's only to get some orthonormal basis, use some theorem, we are using it. Okay, we don't really care what is in L2 0 pi, L2 0 2 pi, apart from this functions. We want to study these functions only. Okay, now this is a Hilbert space, and the proposition is the following. Pn equal to, let Pn P equal to e power int, where n is in R. So instantly I defined orthonormal basis, all that with when I assumed it's countable and I used natural number. You can use integers also, okay? But n going to both the ways, you can formulate the whole thing again. Okay, it will work. Huh? I said if you have a continuous function, it's now. On continuous function, it's now. Then you complete it with respect to that. This is actually not a function space. It's a function space, but actually there's an equivalence class. You assume if it is the integral difference between them, this norm is 0, then they are same. Okay, this is actually you have to quotient it with respect to some vector space where the integral of norm f square equal to 0. These are all, I mean, you use some measure, and then if it is integral is with respect to that measure is 0, then you quotient it with respect. But on continuous function, this is genuine. So we define phi and t equal to e power int, but n coming from integers. In the theorem, I used natural number, but that doesn't matter. I mean, the same thing, everything in the same proof is going to work. There is no difference. Okay, you can replace it with n equal to integer. Then n, I mean, both the ways, norm n going to infinity, the whole thing will work. Okay? You just sum it from minus infinity to infinity, everything will work. Or if you really want, you write integers, index it by natural number and do it. Okay, then the statement is phi n in z is an orthonormal basis. Basis for H. We have already discussed in the after proving Schroeder's theorem. Okay, so I will give it as an assignment. This is another assignment. Okay? But I will orally tell you all the proof. I may even write it. Okay? What has to be done? But you have to write. I mean, there are many steps involved. First, you want to prove it's an orthonormal basis. Okay, it's very easy to check this. Pn, Pm equal to delta. I have to divide it by 1 by 2 pi. Please, I have to use 1 by 2 pi. Then only this will have norm 1. Okay. I mean, integral e power int, if you take the mod, it's 1, and it will give 2 pi, right? So you have to divide it by 2 pi, then you have these things have norm 1. So we need a 1 by 2 pi. I may forget, but sometime, but I mean, you should remember there is a 1 by 2 pi. That constant is there. Up to that constant, everything will work. So you can easily check. If you have phi n phi m, you are going to have e power I n minus mt. Okay, but you can integrate. I mean, this you know how to integrate. Fundamental theorem of calculus. E power something divided by some constant, you will get. that will take the same value at both the endpoints 0 and 2 pi, so it's 0. You integrate it in the +2 integration, okay? That's all. Okay? So this you can do it easily. All you have to prove that this is a maximal orthonormal set, and all you have to prove that this generates. So for that, you have to prove that the summation alpha n phi n, I mean, only you have to prove that span closure of phi n equal to h. That's what you have to prove. Okay. So first you can prove that, but this span closure, this is a norm too. Okay. First you prove that span closure of this phi n. First you check that this is an algebra. Span means summation Cn Pn e power int. Some n equal to some, I mean n in integers. Some you take some, you know, some integers in Cn1 up to something. I mean Cn1, Pn1, something. I mean this may be equal to 0, so minus n Pn you can take. Some of them may be 0. You can take things of this form. You can multiply these two things. This will be again in this form. You can easily see. And constants are there. If you just take every Cn is 0 except at the n equal to 0, except n equal to 0, every Cn is 0. Okay, then its constants are there. And it separates points because e power is is equal to v power it. I mean, e power, yeah, if and only s equal to t in 0 to 2 pi. Okay. So it separates points. So this implies that phi n, this span phi n, closure in the infinity norm equal to c, that c0, whatever. Well, that doesn't work. What you do is you consider this as functions on complex circuit. Okay, that closure, because that's also a compact set. The Stone-Weierstrass theorem that generates the C of the circle. Because here it actually not separate the point 0 and 2 pi, right? They are equal. Phi n of 0 is equal to phi n of 2 pi. The n points they are same, so they don't really separate. See? So you take the circle. The circle it will separate the points. Okay? It's also a compact. You apply Stone-Weierstrass theorem to show that span closure of norm infinity is same as C of that circle. Okay. Now uniform convergence will imply that convergence in that norm, L2 norm. Okay. You can take the limit inside to show that. So that will imply that this span linear closure of this is dense in C of that. But that is dense, I mean, by definition, that is dense in the L2. Okay, so this is dense there. Okay. Some set is dense in something which is dense there, means the set below is also dense. Okay, that's all. So this is the proof. I have given all the details, just write. Okay. Okay, so this is an orthonormal basis for that. Okay. Now we have almost all the theorems of Fourier analysis. I haven't defined what is Fourier series. So suppose if we have a Fn at C0 is 2 pi, okay, then define f hat of n equal to integral of 0 to 2 pi, we have 1 by 2 pi here, of f is equal to just this, f of n. Okay. It's just the inner product between them in this, which is equal to f of, which is just a number. Okay. F of t e power, so the phi n means phi n bar should come minus I n t d. Okay. So we have everything proved in the Hilbert space. I will state that. Actually, this is not what the study of Fourier series, but we get some weaker statement. Okay, so let me state the theorem. Okay, maybe one more. The Fourier analysis, what we are going to do is the following. define. See, the point is this. This is what is called a Fourier transform. You have a function, something here. Then you get a function on f is f hat is a function from z to c. Right? This is discrete, so continuity is not a problem. But in general, if you can consider R, you have to talk about continuity. You can check continuity. It will be continuous. Okay? The Fourier transform will be continuous. So you get a function from here. It will actually vanish at infinity. That's what the Riemann-Leibniz lemma. I will state it again. If the inner product, you know that f pn will go to 0. Pn is an orthonormal basis. So f pn has to go to 0. So f hat n goes to 0. Right? Mod n goes to infinity. Right? We already seen this. So that is precisely, I mean, so it goes to 0 at infinity. Okay. Yeah. That is f hat n. Mod f hat n goes to 0 as mod n goes to infinity. You already seen that, Riemann-Leibniz lemma. Okay. So now f hat is a function. So given a function f, we got a function on this integers. Okay. So whether from this, whether we can reconstruct the function f, that is the question. We cannot always be able to do for any. So if the function is continuous, whether we are able to do that. Okay. So it may not be possible sometimes. So what we can say is the following. Then, so first statement is that. Anyway, I will state it again. Then limit. I have to define again. Define Sn f. You have a f. I define Sn. Okay, which is equal to summation n equal to minus n to n. Okay, f of. See again, some sort of Fourier transform. It's called inverse Fourier transform. What we did is the following. You have a f. Okay, then you have a summation is like integration on that 0 to pi. By integrating f of t with by hitting, I mean by with e power minus int, we got f hat n. So here you have summation in this z. By taking f hat n and again e power f hat n, e power minus int. There we had minus int, so plus int. Okay. By taking this, can you get f back? That is the question. SNF is something defined like that. SNF is a function at t equal to this. You have a f, then I define SNF to be this. SNF at t is just this sum. This the idea is the following. You have a f. By integrating with respect to this e power int, we got a function on integers. Now use this function to get a function of this f, another function, SNF. Okay, for each n you get it. Whether this SNF will converge to f, there is a question. First answer is SNF converges in this L2. Theorem. Then SNF minus, I write it in function theory. Integral limit n going to infinity mod of SNF at t, SNF at t minus f of t, okay, whole square goes to 0. SNF need not converge to this. Of course, if SNF converges to f uniformly, for example, then this will happen, of course. You can take the limit inside and so the question is whether SNF converges to f uniformly. That's one question. Whether SNF converges to f pointwise at least. And all these questions we are going to answer. But here, it at least converges in L2. This statement is always true. Limit n going to infinity, SNF minus this going to 0. So this is the theorem. The proof is just easy. SNF is nothing but as a function is nothing but summation n equal to minus n to n f e n, right? Times e n times e. Sorry, e n f n phi n phi n. Okay? And we know that this converges to f. This is equal to f, in fact. I mean, if you take the summation n equal to minus n, this is equal to f. This converges f in L2. But the convergence is in L2. This SNF converges to f in L2. That is what from Hilbert space theory. This is an orthonormal basis. You take the inner product with an orthonormal basis and write like this. Then this converges to f is the statement in the Hilbert space. That's the property of the, in fact, the definition of orthonormal basis. One of the definition of orthonormal basis. Okay? But the convergence is not pointwise. It happens in the Hilbert space. What this converges to this means precisely this. Some function fn converges to f in L2 means fn minus f norm 2 goes to 0. That is exactly equal to inner product of fn minus f, this integral, the square goes to 0. That is precisely that. Okay? This is exactly the definition. Just think about it. This converges to f in L2. Exactly, this is the definition. So we have this statement. If you have any f in this, then SNF approximate this f in L2. By this, we mean this. This integral between them is that goes to 0. Now the question is whether SNF goes to f pointwise. Number one question for all f in that. Answer is no. So in fact, we can even prove that SNF does not converge at some point. I mean, we can prove that even convergence is not guaranteed. Okay, that is our next goal, and we may not have time for that, but I will make some statement. So this is just a lemma proposition. Right, is just this SNF at t is equal to integral 0 to 2 pi 1 by 2 pi. I just want to do a computation and stop. dn t minus a. This is this kind of integration, what is called convolution. We'll come to that. Okay? dn t minus s f of s ds, where this dn of t equal to sine n plus half. So 2n plus 1 by 2 t we don't have to worry whether it is defined at 0 or something. We are going to integrate. Doesn't matter. Okay. I mean, single point doesn't matter. Okay. And this is called Dirichlet kernel. I mean, what is kernel means some function you use to integrate with something and produce something, some other function. Okay. This is a function. This we are integrating with s. This is a function of two variables, of course, t minus s. So you are integrating with s and you are getting a function of t. Okay. So whatever you do, this is what is called kernel. I mean, a function is called kernel. There is a different kernel. That's different. Okay. So this is what Dirichlet kernel. So we want to prove the statement. This is direct. It's just a computation. We just do that. What is Sn? So this involves F. Sn of F at T. Maybe I can remove this bracket. I call it just Sn. Sn is an operator. Sn of F at T equal to, by definition, summation n equal to minus n f hat n e power I n t, right? That's what it is defined to be. Now this is equal to summation n equal to minus n p n. This is integral 0 to 2 pi. There is a 1 by 2 pi. 1 by 2 pi is there. So there is a 1 by 2 pi. 0 to 2 pi. So f of s e power minus ins times e power int. This is just a constant. You can take it inside. Let me write it here. You can take it here. You get e power in t minus s. Okay. So our dn is equal to dnt. I mean, you get dn of t minus s, where dnt is this summation. That's all, no? I take this e power int inside. So e power in t minus s again. So that is the dn of t minus s. So dnt is nothing but this. Okay. And this is just a geometric term. And the first term is going to be e power minus int r power n minus 1, no? So r power, there are 2n plus 1 term. Okay. So e power I mean the ratio is e power it. So I 2n plus 1 t minus 1, right? Right. So we get e power, so int, so e power I 2n, if you subtract it, it is going to be n plus 1t, right? Minus e power int, e power it minus 1. So I want to get that term. I mean, that sine t by 2 is nothing but e power it by 2 minus e power it by 2. Okay. So I take a e power it by 2 here. I make it, I want to have e power it by 2 and e power minus it by 2 here. So I want to take a e power it by 2 here. So that same thing I want to do it there. So which is going to be e power I n plus half. Okay. I have taken something minus e power I n plus half. I n plus half. Okay. Okay. This is precisely that. We got that. We require this. And I want to first prove that this there exists some continuous function for which the convergence, I mean, the convergence does not happen. Then we will impose some condition and see convergence happen. And there is something called, this is Dirichlet kernel. There is something called Fedger kernel. I mean, there's a you can sum this. You can take the average of this again, Sn again, and that will converge uniform. So I want to prove. Okay? And if we have time, we will do more. So next Tuesday we will not have class. We will meet on Thursday. I know.